Okay, so let's start our limits. When you get into calculus, again, if that's the direction you're going, you'll get a little bit more of a specific or more appropriate or more whatever exact definition of things, but I'm just going to give you the basics of it, all right? When we start our limits, we'll talk more about how they're used, etc., but basically, a limit is the y value. So we're looking at graphs or values, or the output value. We talk about that when we look at points. We have an input, output, an x, y, a rectangular coordinate. A limit is the y value of function appears to be approaching from both the left and the right side of a given x value or input value. And again, this is kind of a little bit wordy and it's very visual when we look at this, at least to start. What we're looking for is, if I put an input into a function and I take the output, does it go to the same place on both sides? Does it connect? Does it connect at a whole? Or is it one of those like piecewise functions where the pieces are broken apart? Or does it end? Is there infinity going on one side? And so we're going to be looking at continuous functions and broken function or non-continuous functions. When I talk about continuous, I mean something that has no breaks, no holes. It just continues forever, as opposed to a non-continuous function where there's maybe a little hole in it, or maybe it's broken, piecewise function. But the limit is all about where it appears to be going. And 9 times out of 10, that's not an exact representation, but a lot of times, the value and the limit are the same if it's a continuous function. And so if I am looking for the value at -3, what I would do is go to x equals -3 and follow this up and find the point and figure out what the y is there. And the y happens to be 4. Again, because this is a continuous function, my y value is 4. Well, the limit has a little bit of a different representation here. What is the limit? That means, where does this function look like it's going on the left and on the right hand side of -3? And it also appears like it's going to 4. So in this case, my limit and my value are the same. Hey, Ashley, why don't you take this? Oops. How was Florida? Good. Now, when I look at a problem like the second one in this first example, I'm just kind of comparing the difference between a value and a limit, and a lot of times the limit and the value are the same. But in this case, I have what I call a hole in the graph, which means that at -3, there is no y value. And so we call this undefined. It is undefined at that location because there's no value. We have a hole in that location where that needs to be. However, my limit is, where does the function appear to go on the left and on the right hand side of -3? And if I just sort of hover up to that, on the left and on the right, both sides point to that hole, right? That hole is my limit. So even though it doesn't have a value, it still goes to that spot. So it's all about coming together at a location, whether it has a value at that location or not. And then sometimes we have a removable value, one that falls out of the function. It's undefined at this location, so we give it a different value. the function is not continuous because it still has this hole and this other value drops out. My value here is 1, but my limit is still 4 because it's still going to that hole on each side. So when does a limit not exist? When does a limit not have a value? When would the limit not be 4? When my function, again, is broken. On the left-hand side, it goes up to 4. On the right-hand side, it goes down to 1. They don't connect. And if they don't connect, we say that the limit is not undefined. We say it does not exist. Does not exist. And you know us lazy math people. We don't write out the word equal. We use an equal sign. We don't write out the word plus, greater than, less than. We don't even write out the full limit here or function. So we're not going to write out does not exist. ENE is a totally acceptable terminology. So whenever we think, or whenever we have a spot where the limit or the sides do not connect, we have a limit that does not exist, because in order for a limit to exist, it's got to go to the same place on both sides, whether it's up, whether it's down. It's got to touch on both sides. It doesn't have to have a value at that location, but it's got to touch at that location. So what is my value here? You guys have seen open and closed circles. When it's open, that means it does not exist at that location. If it's closed, it does. So my value here is at 1. The limit and the value do not have to be the same. They can be, but they don't have to be. As you can see, I can have no value but a limit. I can have a matching value, matching limit. I can have a value that doesn't match the limit. I can have a value but no limit. I can even have no value, no limit. All right? What's my next one? What's the value at -3? Where is there a closed circle? That's at 2. Where is the limit? It doesn't come together, and that's the whole point of limits. So again, I'm going to give you the full definition of a limit, but I'm just going to sum it up. Again, basically, if I have a function and I'm looking for where the limit is headed on that function as it approaches a particular number that's real, like a c, any number c, somewhere that is a value on that, on our coordinate plane. If I can get really close to that c on either side, and as I get really close to that c, sufficiently close is what they referred to, but not necessarily equal to, but I get as close as I can. If I can get as close as possible and I end up being in the same place, then that same place is my limit, and it's some real number that will give as our kind of value. Again, it doesn't have to match the exact value, and if I get close and I don't touch, I can't meet each other on both sides, then I say my limit does not exist. We sometimes also refer to a one-sided limit. Let's say I'm looking specifically only on the left-hand side, where does it appear to be going? Only on the right-hand side, where does it appear to be going? And so we refer to those as our one-sided limits. And we write them a little bit differently. They have a little bit different notation. And so a one-sided limit, again, is the y value. A function approaches, as you approach again or get close to a given x value, from either the left or the right side. So again, our limit is always our y value. If I could put a point to what I'm looking at, the answer to a limit is a y value. What I'm approaching is the x value that I want to look at. So when I talk about approaching from the left, I will put a little negative on there. Do you see that little tiny negative? that represents from the left. And when I come from the left, this is hard for people. I'm not saying that I'm headed towards the left. I'm saying I am coming from the left, okay? So if I could draw a wall around the x value that I'm looking at, if I'm headed this way, that is from the left. So I'm going to be looking in on the left-hand side. I'm coming from the left. And so if I'm coming from the left, I don't have to go very far out because I'm going to get sufficiently close to 3. So I'm coming from the left, so I'm going to start pretty close to 3. And I'm just going to keep traveling and traveling and traveling closer and closer to 3. And what y value does that appear to be headed towards? It appears this point here is 3, negative 1, but it's undefined at negative 1 because it has an open circle. But it doesn't matter that it's undefined as far as a value goes, because my limit is where does it look like it's headed? It's headed towards this hole, and this hole is at negative 1. So that's the difference between a limit and a value, okay? If I am looking from the right, so now I'm approaching from the right. Again, if I could draw that wall at 3, this direction is from the right. Okay? So I'm not headed to the right. I'm coming from the right-hand side. And again, I'm getting sufficiently close to 3. So I'm going to jump to the right a little bit of 3 and then head back towards 3. So I jump to the right a little bit of 3 and then I head back towards 3. Where am I headed? I'm headed to this point right here, which is the point 3, 2. And that it does exist there. So my value is 2. But on the right, my limit is also 2. And so that's how they get this value. This is my limit notation. If I said to you, what is the value of the function at 3? It is where it is solid, and that is 2. Okay, so limits are about where we approach. Any questions so far? Okay. So let's take a look at an example. We're going to go at this picture, and I have all these holes. This is like that scary. What's nice is we're not going to be drawing the piecewise functions just yet, okay? So you don't have to worry about drawing them, but we are going to be looking at them. Do you remember drawing piecewise functions in Algebra 2? Do you remember it making you like a little like, I hate these, because a lot of French people do not like them. So this is, somebody else did the drawing for us, thank them. This is my function, and it's got like all these different things going on. It's made up of all these pieces, and so my leftmost piece of this function looks like it's a line. And it's a line that stops at negative 2 for my x value. And then it appears to turn into a positive parabola. So this is a positive chunk of a parabola. And so that's another little piece of this function. And then all of a sudden it changes directions again, and it's a negative parabola to finish off on the far right-hand side. So this has 3 different pieces, but then on top of that, it also has this foreign value that's floating out below that never even hits on the graph. So it's got all these things going on. Okay, so different values, different pieces. This first one, I know it's sort of hard to see, and I apologize that, but this says x approaches negative 2 from the left. That's what that first thing says. It's really hard to see. I don't know if it's better on yours than it is on my copy. Not really, but that's what it's supposed to say. So I'm approaching negative 2 from the left. So again, this is how I'm doing it. Remember, I'm coming from the left. So I'm on the left-hand side of negative 2, and then I'm walking towards negative 2. So I sort of pick myself off of negative 2, and then I walk back towards it. I stand at negative 2, I jump to the left, and I move back towards it. So where does it look like it's going? It looks like it's going to 1. Beautiful. Now I'm going to do the same thing, and when I talk about being on the function, if I could shrink myself down to tiny person and be on the function, I don't mean be on the coordinate plane. I mean be on the function. So again, I'm on the function at -2, and if I want to find out where I'm headed as I approach -2 from the right, that means I have to jump to the right. I'm going to plummet down to here, and then I'm going to head back towards -2. Where am I headed? This one says x approaches -2 from the right. So again, here I jump down to the right, and then I head back towards it. I'm headed towards this little hole. This hole is at -2. Now, in order for a limit to exist, what has to happen is, on the left and on the right, they need to go to the same exact place. Is 1 the same as -2? No. And because they don't meet together, we say that the limit as x approaches -2 does not exist. It doesn't have a value because these two guys don't match. In order for it to have a limit, I've got to go to the same place on both sides. Again, don't confuse the value with the limit. So now we're going to take a look at 1. Just 1. 1, not from the left, not from the right, 1 in general. So I'm going to focus at 1. And again, if I could draw an imaginary line at 1, and then jump to the left and walk on that function, where am I headed?
1.
To 1. If I could jump to the right and walk towards it, where am I headed? 1. What's my limit? 1. Did they meet? Yes. Did they meet at a value?
No.
No, they met at a hole. So let's jump down here. What's the value? Where is there a solid dot? At -2. Most of the time, again, a lot of the time, often, the value and the limit are going to be the same, especially if the function is continuous. And so the only time I worry about my limit not existing is if I have these breaks and holes in my graph. So if they want me to find a limit as x approaches 0, as x approaches 0, I just got this nice piece of the graph, right? Right here. It's nice and solid. There's no hole. There's no break. There's no nothing. So that means my value and my limit at 0 are going to be the same. And if the value and the limit at 0 are the same, because there's no holes, there's no breaks, what is the limit at 0? I think I hear answers, but did I hear -2? Yeah. Yeah. I heard 2s, but I think I heard somebody say -2. Likewise, as x approaches 3, is there a break? Is there a hole? Is there a disturbance at 3? If I go up to this function at 3, nope, I've got this nice, solid, continuous place. What's my value at 3? What's my limit at 3? They're the same. Yeah. How about -1? Any issue? -3. The value and the limit are the same. It's a continuous piece of the function. No holes, no breaks, no jumps, no disturbances. It's on a solid part. How about -3? What did we say? 0, great. Limits are real easy and nice if there is, again, a continuous piece of the function, if there's no issue. but limits get tricky when we start breaking it up into pieces, okay? All right, now, I'm not looking for a limit at -2. I am looking for a value at -2. We already know that the limit does not exist, but where is the actual value? 1. Nice, because that's where it's a solid dash. Okay, so we have 3 areas where we have limits that will not exist. And limits do not exist when there is a vertical asymptote. What do I mean by that? Yeah.
A point on the y, going up and down.
Yeah.
Where points from.
Yeah, where your graph can't even cross over. And we've seen asymptotes already this year when we graphed like tangent and cotangent, secant, cosecant. So if there's a vertical asymptote, and again, what that looks like is I have this graph and I have this imaginary line that I can't approach on either side. So if I'm looking for a limit for an x value that falls on an asymptote, I know automatically my limit does not exist. A limit also does not exist in how we saw it here. Where did I have a limit that didn't exist? That was at x equals -2. And why didn't it exist? It didn't match on both sides. So I have a limit that does not exist if the left and right side of the function don't meet up. And the last place that we say we have a limit that does not exist is kind of a little bit tricky because we talk about a left side and a right side of a function, a left hand coming from the left, coming from the right. But if I don't have 2 sides of a function, I can't have a limit, technically. And so we say at an endpoint. I do have to sort of star this statement because we are going to be looking at limits as we approach infinity, and infinity is a one-sided situation, and we will give a limit for that. However, it truly does not exist, but we have to kind of work around that, and I'm talking a little bit ahead of the game. All right, let's see if you guys, I want to skip example 4 right now. It's too soon to get into that. But let's see if you guys can kind of answer what we've got going on in this table. Give it a try. See if you can interpret what's going on here. All you have to do is put a T or an F next to whatever one you think, or whether you think it's true or false. Again, is just going to be practicing. As you see, this gets a little weird. So I want to go through and give these a try. I want to do one together. Let's talk through one. Let's make sure that we can read everything here before we commit. This one here is just x approaches -1. It doesn't go from the left to right. This one is x approaches 0. This one is x approaches 2 from the right. Those are values. This is x approaches -1 from the right. X approaches 1 from the left, and X approaches 2 in general. Okay.
It's negative.
For 1A, there's a little tiny negative thing. You can see it better on ours.
Okay. Then let's put that in there. Good. All right. So yeah, I can't see it at all on mine, and I do very much apologize on that. All right. So take a look. I want to approach -1 from the left again, and I'm going to do it in pencil here. I'm going to draw a line at -1. This is just imaginary line. I'm just drawing it there to separate the graph at -1. This is the left-hand side. This is the right-hand side of that line. Left-hand and right-hand side of that line. And so when I'm coming from the left, I'm going to be looking at the left-hand side here. And again, if I could shrink myself down and come from the left, where would I be headed? 3. Super. 3. What's the value, though?
Untimed.
1. Why 1? How come this is a value at 1? That's where the solid dot is, yeah. Yep. Okay. How about the limit as x approaches 0? It's 0. Yep. I don't have to worry too much about it. There's no issue. The limit and the value are the same at 0 because that function is just a continuous line at 0. There's no breaks, no holes, no nothing. It just cuts right through 0. The limit and the value are the same. Okay, how about 2 from the right? Again, I'm going to draw my wall at 2. I've got a left. I've got a right. I'm looking at the right. I heard 1. Let's jump back to value. We're bouncing back and forth all over the place. How do I know if they want a value or if they want a limit? It's all about how it's written. We have to learn how to read the language, the foreign language of math. This is saying, what is the value? What's the y value when x is -1? What's the y value when x is 2?
Undefined.
Ah, come on. Why isn't it 1?
Because it's an open
Because it's an open circle, so there's no value. There's no solid value. Yep. All right, let's go ahead and approach -1 from the right. I'm back here and I'm coming on the right-hand side. Jumping to the right. Where am I headed?
Whoa, where are we?
1. Nice job. Okay, all right. Now I've got to go to 1 from the left. So again, I'm going to draw my imaginary line through 1. I've got a left of that side. I've got a right. I don't care about that. I'm looking at the left. So where am I headed? -1. How about 2? Now this one doesn't say from the left or from the right. So I've got to sort of look at both sides. Surround myself on 2. Does it connect?
No.
No. In fact, I only have a right-hand side. So if it doesn't connect and I'm not looking from the left or from the right, it does not exist. Okay. So I am going to, again, give you a few. Let's do 2. I'll have you guys work through 2. I'll give you time to do this. If you finish early and you're feeling confident, jump on down to 3. But let's do 2. And then we'll check in a little bit.
Just DNF with the wages and then we
Keep calling me a liar.
How did you get 3 of 1? And for B.
For B, because I'm way wrong.
For what?
Yeah, I do not know how I got 3. I'm going to be out. I think I went to -1 instead. This should be undefined, right? Yeah, yeah. Whew. All right, there we
What about
go.
D?
Did I do D bad too? D, -2 from the right. I'm confident on that one.
Wait, what?
Oh, that looks like a 3, not 4. I just can't count.
How did I get 3 for H? The value at -2, that's where it's solid.
3 and 1, okay.
Yeah. Yeah. All right, let it out, guys, let it
I
out.
didn't see that it
Hey, why is D4? This is a -2. So I'm focusing on -2. And again, I'm on the right-hand side. and the right-hand side is heading up again. If I could walk myself on this graph, I would be walking towards that hole. That hole is at 4.
Why is it the ones that closed out?
Because I can't walk on the graph and get there. I have to be able to walk on the graph to get to that place. This is this floater. There's nothing on the right of that point.
So how do you ever get to that point?
I don't.
You can't.
That's just what the value is, and I can never, limit-wise, approach that. Good? Does that make any sense? I have to be able to jump on the graph and walk to it to get there.
Okay.
So that will never be the limit, yes?
Yes, for the specific one.
So typically, if it's a value, it's undefined. If it's a limit, it does not exist. We don't do undefined for limits ever, but does not exist is fair for a value. So you could use D&E for both, okay? All right, pause. Let's do number 3. Anybody have anything to say? Any anger out there? I really regret not having you put your phones away. We won't let that slide anymore. Any questions, any comments?
When's the quiz for test?
No, it might be after Easter break.
Whoa,
Yeah.
not like the day we come back.
No, oh, no, 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 no. But if we can work things out, we might try and get it done before. We'll see. Yeah, we'll see. Okay. No questions on 3? Then let's finish 4 off. Give it a try. There we go. Anybody have a question or concern?
For the first time I didn't like cross out anything to change it because I didn't count.
I got 4 out of 8 right.
Good? Are we okay? Yes.
Done it. This was like 20 minutes.
How is C4? So I'm looking for the limit as x approaches 2. Remember, the limit is where is it headed on both sides of 2.
All in 1 minute.
It's not a value, it's where is it headed. So at 2, right here, at 2, to the left of 2, just to the left of 2, and I want to go just to the left and then head back towards 2, I'm headed towards that hole. Then I want to go just to the right of 2 and head back towards 2, and I'm headed towards that hole. Where is that hole? That hole is at 4. That's why it's there. I'm looking for it to connect on both sides of 2, and that's where it's connected. It's not a value, but that's where the limit is, okay? Hey, when you do your homework today, your homework is not big like this, for the most part. You don't get like 5 different questions from the same graph. You get 1 question from a graph. What is the limit as x approaches blah on this graph, okay? So I'm going to go through the